All right, let's discuss or start our discussion on converting a spring mass damper system to RLC. All right. And you might wonder, why would we do this, right? But, I think, right, that after 98, right, an RLC system, we started learning it about that in 98, or Introduction to Circuits, and differential equations. So we would have seen this quite a bit, right? And we have all these tricks that we can use to analyze circuits that we can then use to analyze our spring mass damper systems. So if that's node 2, right, well, that's just, ZC, ZR plus ZL plus ZC. I'll complete this, right? That's all that is. And we know, SC is 1 over SC, R is ZR, ZL equals SL. Right? Conceivably, if we were trying to match two systems, we could find the Thevenin equivalent, right? What else can we can do nodal, we can do mesh. So all these kinds of EE tricks of the trade, right, we can use on physical systems, right? And one of the physical systems is just, in the book, might be, we have a wheel, right, with a shock absorber in parallel with a spring with a mass, right? So only worrying about the up and down direction. Why? Well, the damper, right, is the resistor. The spring is the inductor, and the mass is the capacitor. And I'm going to get into it a little bit later, but we can have an input voltage and an output voltage. All right. Oh, no, I said that was in parallel, so excuse me. Darn it. So we have the resistor in parallel with the inductor. That goes to the capacitor. Sorry about that. So, this very physical system, right, we can use our circuit techniques, which we're really good at by now, to analyze what's going on. And, even in heat transfer, they use, RC equivalents. In heat transfer, there's no inductor equivalent, all right? And so, yeah, if I have this car wheel with a damper and a mass, right, that's a car. Well, that's all passive like RLC, but you know, we could put an active control system there, right? Because we're heading into the control systems part of the course, all right? And the beauty of controls and why it's important, I'm actually going to save that for next time, all right? But are there any questions so far? Okay. So yeah, I won't make a big deal out of it now, but it seems that attendance is rolling off. All right. So this can be used for more than just cars, right? Here we have a person that we want to see their response to a car seat moving up and down. So we have a lower torso, which is a mass, and human bodies are springy and they're also dampish like. Then you have the middle part, and that's springy and damping light, upper torso, right? Now, yeah, that kind of assumes, though, there's no active control, right? Because people, while you might be springy and might be resistive, you're also changing what you do. So this is it's almost like you're there, but you're not controlling your body. But still, it's a good place to start for some things. All right. So as I said before, you can have a car or some kind of mass spring damper, right, where you might have a wheel, right? Here's, in this case, the spring is in parallel with the shock absorber like I had talked about, right? And so that you can make a circuit with the inductor in parallel with the resistor, right? And then you measure something across the capacitor. Just let me, all right. So talking about strictly up and down, right? Currents, although there's something I think, and I haven't been able to get to the bottom of it, and I'm sorry, but these forces are all coming out of if this mass, right, has a node, right, look, the currents come in, the currents come out. Here, the force comes out and comes out both ways. So I think there might be a problem with this picture. All right. But don't let it get you down. So anyway, what would be the equivalent? Forces, right, is current. All right. Velocity will be the voltage, meaning something, position changing with time, right? Where normally voltage is considered for us, it's kind of static, something between 2 points, right? But the way the math works out, in fact, when you read off a voltage, you're reading actually a velocity, right? Now, mass is mass because look at the equation for force. It's the mass times the derivative of the velocity, right? Now, I'm sure you remember that that's mass times d squared, oops, d squared y dt squared. So when you take a derivative of y, of position, right, then you get velocity. All right. Looking at the equation for force on a spring, well, that's very inductor-like. The damping coefficient, right, you have two, like a voltage is really something, is a voltage difference across a device, Vx minus Vy, right? In this case, this is velocity times a scalar. It just turns out that the damping coefficient is 1 over the resistance, right? And then these, or maybe the pictures, yeah, because if Fc is positive, because it's going up, and these guys, Fs and F down, are going down, then they would be negative. So you would have Fc minus Fs minus Fd. And I think that C really should be mass. I think there's a typo there. Equals 0, right? And then when you move these over, it's positive. Where we talk about the I is positive when going into the voltage terminal of the device, right? And negative, all right? So vertical velocity is voltage, the capacitance straightforward. Inductance, again, it's the same math when we look at changes in velocity, or these are changes in voltage. Here we're doing changes in velocity, right? So even though it might seem a little bit weird that our voltage is actually something changing in time, which doesn't that sound like current, right? Charges per unit time or something. But it's just the way the math works out. So y is position, right? And Vy is velocity, right? And the way they tend to draw these things is that if this is the mass, right, we have we tend to call the velocity of the mass this, then maybe some kind of damper system, and that Vx is some kind of platform moving up and down, right? So there's the position of the platform, which is just x of t. You know, where is this platform, right? Y of t is the position of the mass, right? X of t, position of platform. So this could be an elevator, right? This could be, you know, here's an elevator, right? Here's me in the elevator, right? I'm springy, but I'm also resistive. And let's just say, for instance, I'm modeling it like this, where I have the spring and the damper are in series. And then, yeah, maybe my head or my whole body is the mass, right? So as the elevator moves up, the changing position is given by x. How fast I'm moving is Vx of t, right? That's the platform, but that doesn't necessarily mean my body is, you know, in conjunction with that. But let's just talk about that for a second, right? If I had a platform moving up and down, and I had a mass on top of it with nothing in between, right? Well, then whenever this moved, this would move exactly with it, right? So that would be I'd have Vx, the capacitor, the voltage across the capacitor is equal to the velocity of Vy, right? And you might say, well, there'll be current flow. Yes, but an ideal voltage, whatever this is, will be this. An ideal voltage source can make that current be whatever you want it to be to make the voltages equal, right? And so there is no damping, no whatever. Nothing happens, right? If I have a platform and I have a damper, and a mass, all right, the velocity of that platform is still Vx, but now there's a damper. So dampers are just kind of like resistors. You just draw a resistor, and then the mass, one end is connected here, and the other end of the capacitor is connected to ground, because the velocity of Y, or the velocity of that capacitor, is the output. It's always measured with respect to ground. So when you draw this picture, right, you've always got to have one end of that capacitor tied to ground. Otherwise, it doesn't make physical sense. All right. So really, this is a first order system, right? And so it has a step response, you know, like that. It has a Bode plot like that. And what would a step response be? Well, that's, you know, I'm going 0 meters per second, And then instantaneously, let's say I'm going 1 meter per second. So I immediately accelerate to some constant velocity. Now, we know that that's not, that's mathematical. Step functions aren't physically realizable, but if I had a slope, right, but the time constant of that system was a lot longer than this rise time, it would look like a step response. Okay. If I had a platform and I had a spring connected to a mass, right, and I have the velocity of that platform and the velocity of the mass. Well, the input velocity is the input voltage, just like always. It gets fed into an inductor, right? One end of an inductor has to go to the mass, and one end of that mass, because where is this velocity being referenced to? 0. All right. So what is the transfer function of this? All right. So Vy Vx is really just what? Zc Zl plus Zc, which equals 1 over Sc SL plus 1 over SC equals LC plus 1 . All right. What is this going to do? Right? It's a second order system. So is it over, under, critical? Well, we know all we have to do is look at this polynomial, just like with the op amp, right? Find out whether we have 2 real roots, 1 repeated real root, or 2 complex roots. All right, let's do it. So all I have to do is worry about this part right here. All right, so A equals 1, B equals 0, because there's no S term, and then C equals 1 over LC. So what do we get? The roots equal minus B, so that's 0, divided by 2A, which is 2, plus or minus the square roots of B squared, which is 0, right, minus for LC nope. All right. Which equals plus or minus 2 square root of 1 over LC divided by 2 I, and those cancels. 2 imaginary roots. Critical, it's real and it's the same. This is complex and they're different, right? Because one is plus 1 over LCJ and the other one is minus 1 over LCJ. All right. There's our imaginary. Here's our real. So I get plus square root 1 over LCJ minus. So there's 2. Real would be 2 here. 2 distinct real roots. So that would be over. Under is 2 complex. And that means you have a real and an imaginary part. All right, it's a little, maybe it's a little bit tricky, but that'd be like this, right? There's 2 complex, where 2 real, right? Real is real, right? Complex has both, right? And critical is 2 reals of same value. So that would be here, and I'm trying to draw that there's 2 there. Does that make sense? So as we get more and more imaginary, right, these roots would come in, then they'd be the same, and then they would move up this way. But we don't really have that. What we really have are 2 purely imaginary. So in fact, it's not over because it's got an imaginary part. It's not under, which has a real and an imaginary. It's only got 2 imaginary. And it's not critical because there's not 2 real roots at the same spot. And so in fact, it's none of the above, right? And one thing to say is, you know, pure J, right, usually implies some kind of sine wave, all right? And think about it. If I have energy stored in this inductor, right, it goes into this capacitor. and stores it as charge, right? Then this comes back into the inductor and stores it as moving charge. And then it comes back and forth. But the energy never leaves, right? Power dissipation, right? It's all real. So this just goes back and forth, right? Forever. It never damps out because we never lose any energy because it's ideal, right? Just like if I have a mass on a string and no friction, when it's up here, I'm storing it all in potential energy. When it's down here, it's all in Connecticut. No, sorry, I'm from Connecticut. Kinetic energy, all right? And it would go swinging forever. Now, if there's air friction, oh, there's a damper and it will slowly damp out, right? So this is an uncontrolled system, right? They call it not in control because poles are on the imaginary axis, okay? Right. Critical over and under damped are all on this side of the axis, all right? The real part is less than. Not less than or equal to, less than, right? So let's go back to our equation. So we have something s squared plus 1 over LC. I guess I just like this person's Laplace transforms. So look at this. All right. Some constant, right, divided by s squared plus some other constant. All right. That gives you a sine wave, right? So even though maybe the omega naughts, there's like a missing scale factor there, okay? Right there from the inverse Laplace transform, it's a sine wave, all right? But ZC equals one over SC, but that's really 1 over J omega C, right? It's purely imaginary. So pure capacitors can never dissipate energy. ZL equals SL, but that's really J omega L, right? It's purely imaginary. It can never dissipate energy. So that's why when there's no resistance in this circuit, right, and that's just the natural response. It's true, we were doing this circuit, right? But the natural response of this circuit is when it's equal to 0, the input. So that means we just do this. Well, you can see that that's really the same thing. All right. So far, we've had a platform with the mass, and that wasn't very interesting, right? That was just this. And so the velocities are equal, and you can see that in the nodal analysis, right? The voltage is the same everywhere here. So this input voltage or velocity is the same as the output velocity or voltage, right? We've done a mass with I mean, we've done a platform with a spring and a mass, and that gave us this, all right, which is uncontrolled. So we learned something new, that we can have a second order system over under critically damped. This is a second order system that's none of those. It's just not in control. Now then, I guess the next thing is you have a platform, you have a spring, and then you have a damper, right? No mass. All right, I'll bite. Well, there's no device here. There's no mass, right? So I equals 0. So there's going to be no potential drops, right? And so the position of that end of the damper is going to be this. Now, the thing is yes, mass and dampers have mass themselves. We're talking about a damper with no mass and a spring with no mass, which isn't really physically possible, but you're getting the idea, okay? And then I think we had a damper with a mass, right? We have the velocity of the platform. We have a resistor. And then we're measuring the velocity of that mass from here to here. All right. So this one doesn't really make physical sense. This one isn't really that interesting. This one, while the inductors and capacitors and springs they're not perfectly frictionless, right? Um, the friction can be so small that, yeah, it looks like it's oscillating forever and we would call it out of control. So this one, something interesting, something we might have to take care of. And then, yeah, this just happens to be a first order system. All right. And that's something we can take care of. This would be a first order system, but it's not interesting, right? Let's say this is me on an elevator, right? And that my springiness is in parallel with my resistance. All right. This is really, really simplified because the springiness and the mass is like distributed throughout the body. So it'd actually be really kind of a very complex problem. All right. So the moving platform, the input, the elevator, right? Oops. Is Vx, right? That input velocity. I have a damper, which is a resistor. I have an inductor, a spring, which is an inductor. Both ends are tied to the mass, which is the capacitor. All right. So that's L, R, C. Well, what's the transfer equation, right? Now, this is true, right? But can we tell over under critically damped from here? No. right? I mean, I have to give you some things, right? The mass becomes the capacitor. 1 over the spring constant becomes the inductance value, and 1 over B becomes the resistance. Okay, I tell you that. This equation still doesn't tell me whether I'm over, under, or critical. Although because there's a resistor in there, I'm fairly confident that there's a real part, and it'll cause a pole in the left half plane. All right. So I'm pretty sure it'll be over, under, or critical, but I just don't know which. Now this equation, all right, it's more accurate, right? The C comes from the mass, the L comes from 1 over the spring, the R comes from 1 over the B. But I can't tell over, under, critical. I need to get it into that polynomial format. All right. And yeah, sometimes, what's the best way to go can be hard. So should I multiply that through or not? Let's just see. So SC comes through, 1 over SC, I'm going to get 1, right? Plus S squared RLC divided by R plus SL. Still, it's not in that nice polynomial format where we can use the quadratic equation and find out what's going on. All right. So let's add this up together. What are our two? Oh, well, I was going to do it the hard way, I guess. I mean, I was going to make these the same, add it, but yeah, Artem said, hey, let's just do this. Okay. So forever immortalized in the video that was your idea. Okay, good job. So we get R plus SL. Now, as important as that is, it doesn't determine over, under, or critical, right? Then over here we get R plus SL plus S squared RLC. All right, now we have a choice. Yeah, you can, all right, A equals RLC, B equals L, C equals R. But I really like to get it in that standard, this has a constant of 1. All right. So what I want to do is pull out the RLC, and I'm just going to rearrange it. So if I pull out an RLC, it's going to be S divided by RC plus, I pull out an RLC, that's going to be 1 over LC. Then I have R plus SL. Now, yeah, I could pull out the L here and then have SR divided by L, have the L's cancel, but now it really is in this format, right? And doesn't that look like the parallel RLC configuration, right? I mean, I do it a lot in 101, 98, and 110. So yeah, I've got it memorized. But if you look at the natural response of the parallel RLC circuit, you get this. And you might say, yeah, but actually our inductor, our resistor, they were in parallel, but it was in series with the capacitor. Yes, but the natural response inputs equals 0. So we're right back to that. Okay. And yeah, if you got a question, is this going to be over, under, or critically damped? You can draw this picture, but rather than go through the voltage division, you can go straight, set that to 0. Notice they're in parallel, and then do your nodal analysis or whatever. And all you got to do is find the natural response of what that's going to do, right? Also, anyway, yes, it's also easier to grade. when, but you might think, well, that's just school. What do I really care whether it's easy to grade or not, right? But the thing is, think about being on an engineering team and you're trying to communicate with one another. And if people are used to seeing things in a certain way, right, but you give it like this, it's going to slow the flow of communication. Your team agrees that this is the standard way. Okay, right? But getting things into a standard format, even though, both of these are mathematically equivalent, it's important. Or let me put it this way, I know you know what you're doing. Make it easy to confirm that, right? You could think of exams as me trying to find out what you know and don't know, but I'm really just trying to confirm it because I really think you do know it, right? We're just trying to confirm it in the easiest way possible, or least resource intensive way. So for this moving platform, right, we've done this, right, and we've done this. And this one turns out to be the series. I mean, look at it. These are in parallel. This is in series. This turns out to be the series combination. All right. And really, Vy, Vx would just be Zc, Zr plus Zl plus Zc. And I'll leave you to finish that off. All right. So these are two combinations. All right. Now there's a few other combinations. Is that I have a moving platform. Sorry, and I sometimes forget to draw. I start drawing in the circuit equivalents because the spring really looks like an inductor. All right. So I can have a, I have to draw this a little longer. So this is a mass. I have a damper. I have my moving platform. I have my velocity of the mass, my velocity of the platform. But what if the spring is tied to a fixed thing that can't move? All right. That means the velocity of that end of the spring can't move, or it's zero. Well, that's just ground, right? So this picture then becomes, here's my Vx plus minus. I go through a damper. There's my resistor. I connect to a mass. One end of the mass is always measured with respect to ground. Now, what about the inductor? Well, that's connected to the mass as well. But if it was connected to both sides of ground, it would like be a short. So really, it's like that. It's in parallel. All right. Now, yeah, let's say a tricky thing. This would have the same equivalency. So let's say we have something connected to this platform is moving. There's a damper, there's a mass, there's a spring, and one end of that spring is tied to the roof. Well, it's the same thing. The roof doesn't move. So it's the same thing as having this spring tied here, and you would get the same circuit. Even if I rotated it and then said, and you'd say, yeah, but what about gravity? And you said, well, no, you're at equilibrium. You're not falling or you're on a frictionless surface. It would give you the same thing, except, yeah, maybe the Vx. Well, no, you just define everything the same. All right. Yes, sir. One end of this spring goes to the mass. That's measuring how much the velocity is changing. So that's there, right? One of the spring is tied to ground because it's fixed. So that's there, right? And yeah, one end of the damper is tied to the mass. Now, yeah, it's tricky here because it's tied to two opposite sides of the mass, but mathematically, that's this spot as well. And think about it. I'm drawing the mass like it has area, but really it's like a point mass. It's the same spot, right? It's a mass with no volume, right? These are all idealized components. Like when we do a nodal analysis, right, I have a wire, but it's all the same node. It looks like there's distance. That's only so I can draw it properly. So if I have a resistor, right, and then I have another resistor, right? Mathematically, these are the same picture, right? Because there's no, in a pure nodal analysis, that's a node, there's no voltage drop, it's just a wire, right? But even in this picture, it looks like there's a distance through the resistor. But these RLCs are abstractions of, or simplifications of Maxwell's equations, which does have distance and length and dimensions. So no, whatever happens here happens there in instantaneous time. There is no distance. Now maybe I just muddied the waters there a little bit, but so I'm going to leave that be for now. We have a platform. We have a spring. Oh, sorry. Forget. We have a mass. And now the damper side is fixed. Okay. Still, the position of that goes through an inductor, hits the mass. And like, oh, wait, we've done that before. Yeah, but the resistor hits one end of that mass and it's in parallel. Okay. And so you're getting, there's your dissipative element. But I mean, look at it. What's the natural response of this? Short this to ground. This is in parallel with this, is in parallel with this. Let's go back. What's the natural response of this? Set that to 0. This is in parallel with this, this is in parallel with this, this is in parallel with this. So it looks different, but it seems like most of these natural responses will behave like the parallel RLC rather than the series. All right. Now, on the homeworks and exams, I'll ask you, is it overdamped, under critical? And either you tell me yes or no, you know, what it is, or I'll say, write the equation that will tell me, right? And so in order to have over under critical, it has to be second order, right? Now, you know, on the cover of the book, they had 4 of these, right? Because they were talking about a human in a car. So the thing is I have 1 inductor, 1 capacitor. That's got to be second order, right? I have 1 inductor, 1 capacitor. That's got to be second order. But this whole circuit is fourth order. So ultimately, I'm going to have something on top, but I'm going to have s to the 4th plus a1 s to the 3 plus a2 s to the squared plus a1 s plus a naught. And these are all going to be, you know, the values there. All right. Now you might ask yourself, can I ask you, is this over, under, and critical? And what you would have to do is break it up into 2 second order systems, right? And is this one over, under, critical? And is this one over, under, critical? And it, and so we don't really talk about it like that anymore when it's above second order. We kind of say, are there complex roots or not? All right. So what I'm saying is, on the exams, I've almost told you every problem I could ask on the exam. I've given you every configuration, I think. Now I could draw it funny, all right? But because there's R's in that circuit, so nothing can be here, right? But I can have two sets of complex poles, right? I can have 2 sets of, you know, it's all real, or they can all be at the same, right? I can have 4 all right there, right? But I won't be able to be over here. So, and so when we start talking about higher order systems, and yeah, higher order filters, in fact, you'll see that we'll spread these out. 1, 2, 3, 4, 5, 6. When it's complex, you've always got to have 2, by the way, because you have plus or minus I, right? So this is actually a kind of filter, right? Is it critically damped? Well, no, because there's nothing on the real axis. Is it underdamped? Well, everything is complex. So you could say it's critically damped, but I wouldn't. All right. And that, maybe I'm just getting a little bit ahead of myself. All right. So, right, we have, we have platforms, right, moving up and down. We have wheels moving up and down, right? But we have, I guess I could give you an L and a C, but that's like a trick question because then it's unstable, right? But if you have a mass, a spring, and a damper, it's going to be second, and it's going to be over under critical, right? And yeah, if I did this, oops, sorry, right? There's like ridiculous things. Let's say I put a damper. Here's my mass, right? And the spring is fixed, right? And then I also fixed the mass. Well, I just shorted the mass to 0. Nothing's going to change, right? That's ridiculous. So really those configurations we went over, and we went over one valid first order, and first orders aren't critical over under. It's just one real root with exponential decay. All right. I know that was a lot. Any questions? Oh, okay. So no, so Devin said, so if I say I'm 100 kilograms, right, that would be 100 farads, right? If I say I'm 10 something of a spring constant, whatever those units are, it's 1 over 10 henries, right? If I give you 7 damping coefficient, that's 1 over 7 ohms, okay? So mass, capacitance, uh, the spring constant is the spring, which is an inductor, damper, which is B, is 1 over B, which is resistance. Thank you, Devin. Wait, hold on a second. What is what? All right. Hey, if you gotta go, go, because there is a recording. Okay. So why do poles have to be on left side? Well, they don't actually, but to be stable, they do. Okay. And let's just take this. So if we derive that out, we're going to get H of S equals really omega naught S plus omega naught. The inverse Laplace of that is E to the minus T omega naught, which is, the impulse response, which is exponential decay, right? So it's stable because it goes to a known value, right? Now it's true, there are systems where I can kind of fake a negative resistance. So if I had minus, so that would make that the inverse Laplace of that is E to the plus T omega naught, which is exponential increase, which means it just keeps going on forever. All right. 1 over S is really in the time domain. You're integrating something. And so if this is even a constant, right, it's going to keep integrating that forever. If it's a negative constant, it's going to integrate it negative forever. So the thing is this will go out of control. Oh, sure, I could turn the input off and on, but the input doesn't control the system. This is the system. So anything with on that, anything where the real part is greater than or equal to 0, you're going to get exponential increase, or it'll turn into an integrator, right? And yeah, if you have 1 over S squared, it's double integrator, right? You will get a system out of control, which really is going to be next time. But just to give you a taste, right? Here's a system. I have a mass on a pendulum, and if I get off a little bit, the gravity's going to, right now the gravity's pulling straight up and down. It doesn't move. A little bit of noise, and the gravity will, this will move. The gravity will drag it, and then drag it more, and then drag it more, and then keep dragging it. And so, yeah, you get this kind of transfer function for an inverted pendulum. It's time to go. All right. Good questions. And we'll have a lot more fun on Monday. Okay.